Welcome! In this session, we'll explore the problem titled Minimum Number of Steps to Make Two Strings Anagram. This is an interesting problem that dives into the concept of anagrams and string manipulation. We'll break it down step by step and discuss efficient approaches to solve it. In this problem, we are working with two strings, S and T, both of the same length n. The goal is to transform the string T into an anagram of S. Now, an anagram means rearranging the characters of one string to match another, using all the original letters exactly once. To achieve this, we are allowed to perform one operation repeatedly, replace any character in T with another character. The challenge is to determine the minimum number of such replacement steps required to make T an anagram of S. The input consists of two strings, S, which is the target string, and T, which is the string we need to transform. The output will be an integer, representing the smallest number of steps needed to make the transformation. For example, consider the input where S is BAB and T is ABA. Here, the output is 1. This is because we can replace the first character of T, which is A, with B. After this replacement, T becomes BAB, which is an anagram of S. Now, take another example where S is LeetCode and T is practice. In this case, the output is 5. This is because we need to make 5 character replacements in T to match the character counts of S. This demonstrates how the number of steps reflects the effort required to transform T into an anagram of S. Let's break down the transformations for the second example. To turn practice into an anagram of LeetCode, we replace P with L, R with E, O with E, I with T, and C with O. After these 5 replacements, the string T becomes LeetCodeO, which matches the character counts of S. This verifies that 5 steps are necessary. In contrast, if we consider an input like S equals anagram and T equals manger, no steps are required because T is already an anagram of S. Thus, the output is 0. Now, let's discuss the constraints and edge cases. First, the length of both strings is equal, denoted as n, and it ranges from 1 to 100,000. Both strings consist of lowercase English letters only. For edge cases, if S and T are already identical, the output is 0, because no transformations are needed. If the two strings have no common characters at all, the output will simply be n, since every character in T will need to be replaced. For single character strings, the output is 0 if the characters are the same, and 1 otherwise. Finally, given the potential for very large input sizes, it's important to ensure that the solution is efficient and handles up to 100,000 characters within a reasonable time frame. To solve this problem, we start by considering possible approaches. The brute force method involves generating all permutations of the string T and checking if any of them match the string S. However, this approach quickly becomes impractical because the number of permutations grows factorially with the length of the string, meaning even a string of length 10 would require over 3.6 million permutations. This exponential time complexity makes it computationally infeasible, and we discard this approach. Instead, we turn to an optimized method using frequency arrays. The key insight here is that anagrams share the same character frequencies, so rather than focusing on rearranging the characters in T, we can shift our focus to identifying and addressing the mismatched character counts between S and T. We do this by constructing two frequency arrays, one for S and one for T, each containing the counts of every letter from A to Z. By comparing these arrays, we can calculate how many characters in T need to be replaced to make it an anagram of S. This process involves iterating over the strings to populate the frequency arrays, and then iterating over the fixed size arrays to compute the mismatches. Since these operations are linear in nature, this approach achieves a time complexity of O(n), which is a significant improvement over brute force. Now, let's delve deeper into why we choose the frequency array approach as our strategy. This method is both efficient and intuitive, as it directly addresses the problem's requirements without unnecessary computations. The breakthrough here is realizing that we don't need to explicitly rearrange the strings or generate anagrams. The solution lies in simply identifying the mismatched frequencies. This approach optimally balances simplicity and performance. Unlike the brute force method, which is computationally prohibitive with its O(n) complexity, the frequency array approach achieves linear time complexity, O(n), making it much faster. Additionally, compared to a sorting-based solution which involves sorting both strings and comparing them, with a time complexity of n log n, the frequency array method is more efficient. Although it requires extra space for the frequency arrays, this space usage is negligible because the arrays have a fixed size of 26, regardless of the string length. This makes the method both scalable and practical for this problem. Ultimately, the frequency array approach stands out as the best choice due to its superior time complexity and its direct alignment with the problem's requirements. The ability to focus solely on mismatched character frequencies allows us to solve the problem efficiently, without the overhead of unnecessary computations like generating permutations or sorting. This method strikes an ideal balance between performance and simplicity, making it the most effective strategy for determining the minimum number of steps needed to transform one string into an anagram of the other. To solve this problem, we need to determine if the string T is a permutation, or an anagram, of the string S. A permutation simply means that T must contain the exact same characters as S, with identical frequencies, though the order of the characters can differ. To achieve this, we will use an optimized frequency count approach instead of inefficiently generating all possible permutations. The idea here is straightforward: two strings can only be permutations if they have the same character counts. The first step involves checking the lengths of S and T. If their lengths differ, we immediately know they cannot be permutations. Next, we count the frequency of each character in S. This can be done by iterating through S and storing the counts in a dictionary called frequency_map, where the keys are the characters and the values are their respective counts. This gives us a clear picture of how many times each character appears in S. Once we have the frequency map of S, the next step is to verify these counts against the characters in T. For each character in T, we decrement its count in frequency_map. If we encounter a character in T that is not in frequency_map, or if its count becomes negative, then T is clearly not a permutation of S, and we can return false. After processing all the characters of T, we perform a final check to ensure that all the counts in frequency_map are 0. This confirms that every character in S was matched exactly by a corresponding character in T. The key insight here is that matching character frequencies is a simple yet powerful way to determine if two strings are permutations. By modifying the counts dynamically in a single map, we avoid the need to create separate frequency maps for both strings, saving both memory and computation time. Additionally, the algorithm halts as soon as a mismatch is detected, improving efficiency by skipping unnecessary steps. When implementing this algorithm, it's important to account for edge cases. For example, if both strings are empty, they are considered permutations, and we should return true. On the other hand, if the lengths of the strings differ, we can handle this early by immediately returning false. Another thing to consider is case sensitivity. Uppercase and lowercase letters should be treated as distinct characters. For instance, a and a are not the same, so the algorithm must respect this distinction. The primary data structure we use in this approach is a dictionary, or hash map, which efficiently stores and retrieves character counts. With an average time complexity of 1, for insertions and lookups, dictionaries allow us to implement the solution in a highly efficient manner, making them an ideal choice for this problem. Now let's analyze the complexity of this algorithm. For time complexity, the first step involves counting the characters in S, which requires a single pass through the string, taking n time. The second step, verifying the characters in T, also requires a single pass, contributing another n. Therefore, the total time complexity is n, where n is the length of the strings. For space complexity, the dictionary we use to store character counts requires k space, where k is the number of unique characters in S. However, for most practical scenarios, such as when the strings consist of English letters, the number of unique characters is limited to a fixed value, such as 26 for lowercase or uppercase letters. This means the space complexity can be considered 1 in such cases. Overall, the algorithm is both time and space efficient. Let's walk through an example to visualize the algorithm. Suppose S is listen and T is silent. First, we count the frequencies of each character in S, resulting in the frequency map L1, I1, S1, T1, E1, N1. Next, we process each character of T. For the character S, we decrement its count in frequency_map, reducing it to 0. We repeat this for each character in T, such as I, L, and so on. By the end, all counts in frequency_map are 0, indicating that T used exactly the same characters as S. Since no mismatches were found in frequency_map is empty, we determine that S and T are permutations, and the algorithm returns true. This step-by-step process highlights how the algorithm ensures correctness while maintaining efficiency. This Python solution computes the minimum number of steps required to make two strings S and T anagrams of each other. The main idea is to calculate how many characters in S need to be replaced to match the character frequencies in T. The program starts by importing counter from the collections module. This utility is used to count the frequency of characters in both strings. The counter object provides an efficient way to compare the frequency of characters. The minSteps function takes the input strings S and T and begins by constructing frequency counts for both. Count_S represents the frequency of each character in string S, and count_T represents the same for string T. A variable steps is initialized to 0. This will store the total number of characters in S that need to be replaced. The algorithm iterates through each character in count_S. For each character, we check if it exists in count_T. If the character exists, we calculate the excess count in S that is not balanced by T using max, 0, count_S, char, count_T, char. This ensures that we only count the extra characters in S. If the character does not exist in T at all, we add all occurrences of the character in S to steps. Finally, the function returns the total steps value, which represents the minimum replacements needed to make S and T anagrams. This approach is efficient, with a time complexity of O(n), where n is the length of the strings, since counting and iterating through the characters is linear. It also has a space complexity of O(1) if we consider the alphabet size to be constant. Here, we are implementing a solution to calculate the minimum number of steps required to make two strings anagrams of each other. First, we import the required Java utilities and declare the solution class. Inside it, we define the minSteps method, which accepts two strings, S and T. The first step is to create two frequency arrays, counts and county, each with a size of 26 to represent the 26 lowercase English letters. Next, we iterate through each character in string S and increment the corresponding index in counts based on the character's position in the alphabet. Similarly, we loop through string T to populate the count T array with its character frequencies. With these two arrays, we now have a complete breakdown of how often each letter appears in both strings. To compute the number of steps required to make S an anagram of T, we initialize a variable steps to 0. Then, we loop through all 26 indices in the frequency arrays. At each index, we calculate the excess characters in S that are not balanced by T using the formula math.max, 0, counts, I, county, I. This ensures that we only count positive differences, as negative values would indicate that T already has enough of that letter. We add these differences to the steps variable. Finally, after iterating through all characters, the steps variable contains the total number of changes required, and we return this value. This method ensures an efficient solution with a time complexity of O(n), where n is the combined length of the two strings. To solve this problem, we start with an example where S equals BAB and T equals ABA. The goal is to determine the minimum number of changes required to make these two strings anagrams. First, we create frequency counters for both strings. For S, the counter shows B appears twice, and it appears once. For T, A appears twice, and B appears once. Next, we initialize a variable called steps to 0, which will keep track of the total changes needed. Now, processing each character in the frequency counter of S, we start with B. Here, S has two B's, but T only has one. The difference is 1, so we increment steps by 1, making it 1. Next, for A, S has one occurrence and T has two. The difference is negative, meaning there's no need to adjust for excess in T, so steps remains 1. After processing all the characters in S, the total number of steps required is 1. This is our final result for the first example, so the output is 1. Now, let's explore a second example where S is LeetCode and T is practice. We begin by creating frequency counters for both strings. The counter for S shows 3 E's, one each of L, T, C, O, and D. For T, the counter shows one occurrence each of P, R, A, C, T, I, and E. With these counters ready, we initialize steps to 0 once again. Our task is to process the characters in S to compute the minimum changes needed. We now process the characters in the frequency counter of S, starting with L. We see that S contains one L, but T has none. This requires one step, so we increment steps to 1. Moving to E, S has 3 occurrences, while T only has 1. The difference is 2, so we add 2 to steps, updating it to 3. For T, both strings have exactly 1 occurrence, so no changes are needed, and steps remains 3. Similarly, for C, both S and T have 1 occurrence, so we don't make any changes here either. For O, S has 1 occurrence, but T has none, meaning we add 1 step, bringing steps to 4. Next, we process the character D. Here, S has 1 occurrence, while T has none. This requires 1 additional step, so we increment steps to 5. With all characters processed, we calculate the total number of steps needed, which is 5. This is our final result for the second example, so the output is 5. Now, let's analyze a third example with S equal to anagram and T equal to manger. As always, we start by creating frequency counters for both strings. The counter for S shows 3 A's, and one each of N, G, R, and M. For T, the counter shows 3 A's, 2 M's, and one each of N, G, and R. With these counters ready, we initialize steps to 0. We then process the characters in the frequency counter of S, starting with a. Both strings have 3 occurrences, so no changes are needed, and steps remain 0. For N, both S and T have 1 occurrence, so again, no steps are required. Similarly, for G, R, and M, the counts in both strings are equal, or the excesses in T, meaning no changes are needed for these characters either. At this point, we've processed all the characters in S, and steps is still 0. Since there were no excess characters in S that needed to be adjusted, the total number of steps required for this example is 0. This is the final result for the third example, so the output is 0. With all examples complete, we can see how the algorithm efficiently calculates the minimum number of changes necessary to make 2 strings anagrams by focusing only on the excess characters in the first string. To analyze the time complexity of the solution, we start with the operation of counting character frequencies using the counter function. When we create counter S and counter T, the function iterates through each character of the strings S and T. If the length of each string is n, then each counter call takes O(n) time. Since we perform this operation on both strings, the total time for this step becomes O(n) plus O(n), which simplifies to O(n). Next, we have the iteration over the unique keys in count_s, which represents the characters present in string S. The number of unique characters is limited by the size of the alphabet, which is a constant value of 26 for lowercase English letters. For each unique character, operations like dictionary lookups, comparisons, and arithmetic are performed, all of which take constant time. Therefore, this step contributes an O(1) complexity for each character, and since the alphabet size is fixed, the overall complexity remains O(1). In the next step, we calculate the excess characters for each unique key in count_s using the expression max, 0, count_s, char, count_t, char. This is a simple arithmetic operation performed during the loop, and since it runs in constant time for each character, it does not affect the overall complexity. When we combine all these operations, the total time complexity is determined by the most significant term, which is the O(n) complexity of the counter operations. Thus, the final time complexity of the solution is O(n), where n is the length of the input strings S and T. Now, let's examine the space complexity. The counter objects, count_s and count_t, store the frequencies of each unique character in the strings. In the worst case, both counters store up to 26 entries, one for each lowercase English letter. Since this number is constant and does not grow with the input size, the space used by the counter objects is O(1). Additionally, the variables used in the algorithm, such as steps and the loop variable char, also require constant space. Considering all these factors, the overall space complexity of the solution is O(1), because the space required is bounded and does not depend on the size of the input strings. This leads us to the final space complexity of O1. To put this in perspective, we can compare this optimized approach to a brute force solution. A naive approach might involve generating all permutations of one string and comparing them to the other string. This would result in a factorial time complexity of O(n), which becomes computationally infeasible as the length of the strings increases. In contrast, the current solution is highly efficient, reducing the problem to counting excess characters and achieving O(n) time complexity and O(1) space complexity. This makes it well suited for handling even long strings effectively. Finally, let's analyze the best, average, and worst-case scenarios for the algorithm. In the best case, the time complexity is O(n), and the space complexity is O(1), as the algorithm always processes each character in the strings and uses constant space. Similarly, in the average case, the algorithm still iterates through all characters of the strings, maintaining O(n) time and O(1) space complexity. Even in the worst case, where all characters are unique, the algorithm still performs in O(n) time and O(1) space. To formally verify the big O complexity, we note that the counter operations require one full pass over the input strings, resulting in O(n) complexity. The additional loop over the fixed size alphabet contributes O(1). When we combine these, the overall time complexity becomes O(n) plus O(1), which simplifies to O(n). Since the memory usage is constrained by the constant size of the alphabet, the space complexity remains O(1), completing our analysis of the algorithm's efficiency. When tackling this problem, it's important to be mindful of some common mistakes that can trip you up. One frequent oversight is neglecting edge cases, such as handling empty strings or strings with repeated characters. These situations may seem minor, but missing them can lead to runtime errors or incorrect outputs. Another common error is confusing permutations with subsequences. While permutations require the exact same characters in the exact same frequency, subsequences allow characters to be skipped, which is fundamentally different. Additionally, some might only check if two strings are of the same length without verifying their character frequencies. For instance, ABC and ABD are the same length but clearly not permutations. Finally, some implementations are unnecessarily inefficient, like generating all possible permutations of a string, which has a factorial time complexity and quickly becomes impractical for larger inputs. Recognizing these pitfalls early can help you avoid unnecessary frustration and ensure your solution is both correct and efficient. Another mistake to watch out for is ignoring case sensitivity or non-alphabetic characters. For example, assuming that all input strings consist only of lowercase letters can lead to incorrect outputs if the problem involves uppercase or special characters. Always pay close attention to the problem's specifications. Now, from an interview perspective, one of the most essential insights is to focus on character frequency matching. Using a hash map or an array to compare character counts is often the most efficient approach. Recognizing that this problem is a variation of the classic anagram check problem can also be helpful, as it means you may already be familiar with optimized solutions. While sorting both strings and comparing them works, you can achieve a better time complexity of O(n) by using the frequency count approach. Also, remember to clarify the requirements with your interviewer, such as whether the problem is case-sensitive or whether non-alphabetic characters need to be considered. This ensures your solution aligns perfectly with what's expected. This problem shares similarities with several related problems that you might encounter in coding interviews. For instance, valid anagram on LeetCode asks you to determine if two strings are anagrams of each other, which is directly related. Group anagrams involves grouping strings that are anagrams into clusters, which builds on the concept by requiring you to handle multiple inputs. Another variation is find all anagrams in a string, where the goal is to identify all starting indices of substrings that are anagrams of another string. Finally, check permutation asks whether one string is a permutation of another, which is a stricter variation requiring you to focus on the exact arrangement and frequency of characters. Exploring these problems can deepen your understanding of character frequency-based algorithms and strengthen your ability to adapt to different variations of the anagram concept. There are multiple ways to approach this problem, each with its own trade-offs. The sorting approach involves sorting both strings and comparing them. While it's simple to implement, its time complexity is O(n) log n, which can be slower for very large strings. A more efficient method is the hash map approach, where you count character frequencies using a hash map or an array. This reduces the time complexity to O(n), but requires extra space for storing the frequency counts. Another alternative is the sliding window technique, which is particularly useful for checking permutations in substrings. This method uses a frequency array and a sliding window to efficiently check for matches, also achieving O(n) time complexity. However, it can be more complex to implement. Choosing the right approach depends on the specific requirements of the problem, such as whether you're comparing entire strings or looking for substring permutations. Great job! To wrap up, we've covered the key aspects of solving this problem, explored different approaches, and learned some valuable techniques for string manipulation. Keep practicing, and we'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!